Hello everyone, I'm Luca and I'm presenting to you FlexiViT, an improvement to training good old plain ViT models that I developed together with all of these nice people. Every single one of them did significant technical contributions. In a very short summary, we suggest a change in the training of ViT models such that at test time they can run at various different patch sizes. Um, what this means is that, looking at the right hand side here, for example, we end up with one single model, let's call it FlexiViT B, which is represented by this green dashed line, which can run either or anywhere between a fast and okay model all the way to a slow and really strong model. Specifically, it outperforms the best ResNet 50s there are, efficient at V2, and Diet 3 models. We open source them all. Now, for the somewhat longer story, I'll start with a bit more background and motivation. One of the things we noticed over time is that for ViT models, compute is a very good predictor of performance. And there's different ways that are commonly used to change compute of a ViT model, for example, changing its depth or width or MLP size. However, one way which is especially interesting is mostly ignored and overlooked by the community, which is the patch size. Because if we, for example, shrink the patch size by 2 or 2 square, then the attention compute grows by a factor of 16. So patch size is actually a lever with which we can change the compute significantly without changing anything else in the model. Um, Furthermore, um, we have some experiments that show that, for example, the VIT-B model spans a wide range of models from fast and okay all the way to slow and really strong. For example, VIT-B32 is roughly equivalent to a ResNet 50. VIT-B16 is quite a lot better, and VIT-B8 is even better, actually outperforms VIT-L16 and is equivalent-ish to a ResNet 100. No, it's even larger than a ResNet 152 by 2. And the only thing that changes between these models is the patch size, aka sequence length. Uh, Another thing to keep in mind is that in the original VIT paper we already showed that the position embeddings uh, actually learn a nice structure such that they can be simply resampled or resized into position embeddings for different patch size. Because keep in mind, if you change the patch size, you have more patches, and each patch needs its own position embedding. So here's an example that shows the position embedding from B32 being resized to B16, and that just works. And finally, when we noticed over time that for any setting where we use WITs, we usually train a whole family of them. Like we train with B32, with B16, with L14. We train at different resolutions like 2 to 4, 384, 518, and so on. So over time, we started wondering, could we potentially spend the whole range um, of of this quality performance trade-off with a single model with a single set of weights? And the answer turns out to be yes, we can. It works, and it's actually quite simple. And it's the reason I'm here, which is FlexiViT. I'm first going to show the key result and then how to get there. This plot shows on the x-axis the inference time patch size or sequence length. So on the right hand side, we have patch size 8, so it's a heavy model. On the left hand side, we have patch size 48, so it's a lightweight model. And is this with B? The green line is FlexiViT B, and the y-axis is how well it performs on some task. Um, and here we can show that, first of all, FlexiViT performs well across the range compared to individual VITs like VIT-B16, VIT-B30 that performs well at its patch size, but then deteriorates very quickly as soon as you move away from the patch size. And most importantly, we can see that FlexiViT actually matches the VIT trained at the individual patch size each time. So this is great. Um, Now, how to get there? This is super simple actually. For each mini batch during training, we randomly choose the patch size to use. For example, let's say 8. Then to process that mini batch, we take the patch embedding vector or weights, the ones that are actually learned, that are some predefined hard-coded size, like let's say 32 by 32. Then we resize them to 8 by 8 and pass this and use these resized patch embedding weights in order to embed the patches. And we backprop through this resize. Same story for the position embeddings, and that's the only changes that are needed during training. And the result is the FlexiViT, uh, which handles all kinds of patch sizes that it sees during training. Then we show that this does not just work for supervised pre-training, but actually for all kind of trainings where you use a plain VIT. So, for example, in open world detection with all VIT, we flexify the detection training, and it just works. Same story here. The flexi all VIT performs as good as fixed patch size all VIT at the different patch sizes. Same story for image text models like lit and clip, and same story for transfer learning too. And there is actually a lot more in the paper or at the poster. For example, one very nice connection to distillation, that if you use FlexiViT mechanism during distillation, you can initialize the student model with the teacher weights if you use the teacher as the most powerful, smallest patch size model. And then you get a huge head start in distillation and everything works much nicer. More details in the paper. Um, we also can use FlexiViT mechanism to fine-tune models in a much faster way by fine-tuning them at the large patch size. We can use it to pre-train faster. We also have a lot of different types of analysis to try to understand and see what's going on in the model. We have tons of applications with different ways that we could have made with flexible, but that work much worse. Like for example, flexible depth, flexible stride, uh, and we open sourced the code and a whole bunch of pre-trained models in the Big Vision repo that you can find on GitHub. So that's it. See more in the paper or see you at the poster. Thank you.